In this video, we're going to be talking about the atom and what is in it. So before we do that, we want to talk about where we find symbols and numbers to figure out what's in an atom, and that is on our periodic table. So one thing you need to notice is that on the periodic table, the first letter is always capitalized, and if there is a second or third letter, those letters are lowercase. And an example, take a look at your periodic table. If the letters are single letters, it's just one capital. If they have double letters, then the second letter is always going to be lowercase. And if they have three letters, like these guys over here, which is really just a code for we haven't determined what their name or symbol is yet, that's why they have three, everything after the first are going to be lowercase. Now, the reason I mention that is the Regents likes to bring up, and chemistry in general, they like to play these games at this level, is the difference between CO and CO. So if you look at these three on the right, these are going to be cobalt, polonium, and lead, and this would be carbon and oxygen, phosphorus and oxygen, phosphorus and boron. So because these two are capitalized, these three on the side, on the left, they are both capitalized, they're going to be compounds. Therefore, they can be decomposed. Whereas if I give you the ones on the right, since the second letter is lowercase, that's actually going to make them an element, and therefore they cannot decompose. So you've probably already seen those types of questions on some multiple choice, but they do like to play games with that. Now, as far as the atom goes, this pretty much summarizes everything that's in the atom. So we have three things: protons, neutrons, and electrons. If we look at the protons and neutrons, since they are found inside the nucleus, they can be also called nucleons. A nucleon is anything in the nucleus. Since P's and N's are in the nucleus, they're nucleons, electrons are not. We don't call them nucleons. It's that simple. So in the nucleus, or outside the nucleus. You can also say that they are in the orbital, so for the electrons, which is outside the nucleus. So either one works. Charge: proton, positive; electron, negative; neutron, neutral. That's what they're named after for the most part. Mass: 1, 1, and 0. So protons weigh 1, neutrons weigh 1, electrons weigh nothing. Now, that's not actually true. They do have a weight. They are about 2,000 times lighter than the mass of a proton. So that is another way of saying it. We call it 0 because if you were to round 1/2000th to the nearest whole number, it would obviously round down to 0, which is why we do it. But be aware they do have some weight, and so therefore you can't say that their weight is truly 0. It depends on the type of question that they're asking. For the purposes of the weight of the atom, we assume it's 0, but if you're just talking about the actual weight of the electron, it does have some weight, although it's very small. And then symbols: lowercase p, lowercase n, lowercase e. I like to write it with a little negative sign. If you write the negative sign enough, you'll always remember that the electron is the negative one. So that's pretty much what's in an atom. Now, a couple things we need to talk about. The atomic mass unit, abbreviated AMU, which used to be an acceptable unit and no longer. The real unit for the atomic mass unit, otherwise known as the AMU, is the U. So that is the unit of atomic mass units. It's like just like in mass, we measure things in grams, so we use grams as the unit for mass. U is the unit for atomic mass. It's basically a specialty unit that was designed for weighing atoms, because working in grams or kilograms is just too cumbersome because they're so small. The exponents would be, 1 times 10 to the negative 20 something, and so it's just too difficult to use. So we made up a new set of weight just to make adding up atoms easy. Used to weigh atoms, and it's based on 1/12 the mass of carbon-12. So be careful of that. You will get questions on that. It's 1/12 the mass of carbon-12, not 1/12 the mass of carbon-14, not 1/12 the mass of nitrogen-12. It's specifically carbon-12. And if you take carbon-12 and divide it by 12, you get 1, and that's the AMU. I will explain more why they use carbon-12 and not other elements later on in this unit. So if we look at a symbol on the periodic table, there is a couple things we have to be aware of. The number in the top left-hand corner is called the mass number. It can be called the atomic mass or the atomic weight. Any of those three things is acceptable. It is the mass of the atom. It's the P's and the N's added together. Bottom number, that's called the atomic number. It represents the protons alone. It identifies the atom, just like a fingerprint or DNA, and it never changes for the same element. In other words, carbon will always have a 6 in the bottom left. If it does not have a 6 in the bottom left, it is not carbon. And if it does not have a 6 in the bottom left, it can never be if it's a number other than 6, then it can never be carbon. So the bottom left number is what identifies it. The mass can change, because if you notice, I said protons identify it, neutrons don't. You can have different numbers of neutrons. Now, if you look at these numbers and you know that this is P and N added together, this is P alone. If you want to find just neutrons, you subtract. So 12 minus 6 would be 6. So this carbon would have 6 neutrons. Be aware, it is also found on your periodic table. They call this top number right here the atomic mass. Notice it has a decimal point. You are always going to round that to a whole number, or the nearest whole number, until I tell you otherwise. We will eventually know what the decimal means. Right now, we're going to ignore it. And this bottom number here is called the atomic number, and that is your proton number. Don't worry about these numbers in the top right-hand corner. We'll get to them eventually, not for a while. And don't worry about the configuration. We will get to it eventually. But the key is here. It does tell you what they mean. I would highly recommend doing this on your reference table. Writing that in so that way you will never forget it. P plus N and then P alone. Let's go to the next page. So for this page, we have some practice problems. Now, obviously I'm going to show them all to you. So isotope. Isotope is a new word. It has a couple definitions. They all mean the same thing. You can say it the same way. It doesn't really matter. An isotope is when you have the same element, like these three here are all the same element. They're all neon, but they have a different mass. And if you notice, the number in the top left-hand corner is the mass. Their masses are different. It's that simple. There's another way of saying it. You could say it's the same atomic number, in other words, the bottom numbers, which is the same thing as saying the same element, okay? And you could say a different number of neutrons, which is what causes the mass to be different. So saying this first one, it means this. They're no different. And you could simplify it even further and say same P, different N. And the reason? The proton number is the atomic number, which is the element symbol. The neutron number is what causes the mass to be different, which therefore makes it an isotope. So I don't care how you say it, but that's three different ways of saying the same thing. So if we look at these three neons, right, we have one more thing we have to introduce called formal name. So the problem is I don't want to call all three of these neon and then not have a distinction between them because they have different weights and therefore they have different neutron numbers. What does that mean to us? Well, normally, if it wasn't anything major, then maybe we wouldn't care, but turns out this first one is neon. It's the stuff you see in neon tubes, and these two others on the right are neon, but they're radioactive, and you don't really want to hang around them. So there is an important need to distinguish between these because sometimes you get a radioactive version and then a non-radioactive version. So we have what's called the formal name, which can also be called the isotopic notation. The reason? They're isotopes, and it's how we make note of their differences, hence the term isotopic notation. It's an older term, but it is still around. And it's real simple. We just say, well, what's different about them? Their weight. So in the name, I'm going to include the weight. Neon 20, neon 21, neon 22. It's that simple. For protons, since they're all neon, they're all 10. And their neutrons, I would just subtract 20 minus 10, 21 minus 10, 22 minus 10. And that's how I got my neutron number. You could try the next one on your own. I'm just going to skip right to it. There is one question that I do want to go over. So here I have three calciums. Calcium 40, because it weighs 40. Calcium 41, and calcium 40 again. Now, there's their formal names. They all have 20 Ps, and they're going to have 20, 21, and 20 neutrons. Now, the question is, which ones are isotopes, right? Turns out there's two answers, or which two of them are isotopes, right? There are two answers. You could say the first two are isotopes, because in order to be an isotope, remember, you have to be the same element with a different mass. So you could say the first two are isotopes. You could say the second and the third are isotopes, but what you cannot say is that the first and the third are isotopes because they do not have a different mass. They are the same element, but they also have the same mass. So we would just say they're the same thing. They're not isotopes of each other. So that's isotopes. Next thing we're going to introduce is the electrons. So electrons are used for charge. They're used for lots of things. They're going to become very important later on, but for right now, we're just going to say that they are used to determine charge. Think of it this way. Since the atom has protons that are in the nucleus, right? Think of the protons as being in like a lockbox. So the nucleus is not going to let protons or neutrons out very easily. Very rarely does that happen. It does happen in special circumstances. We'll learn all about it, but it does not happen under normal everyday circumstances. The electrons are in orbitals. They are not being held onto as tightly. So it turns out atoms can exchange electrons much more easily than they can exchange protons or neutrons, okay? So much more easily that I would go as far to say as under normal circumstances, they will never exchange protons. They'll never gain or lose protons or neutrons for that matter. It's only electrons that get changed. So now we have this unique situation. If you gain electrons, you're going to gain negatives. That makes you negative. And if you lose electrons, you're going to minus minuses, which will make you go positive. Everyone messes that up. And so be very careful there. The formula that I want you to use is right here. P minus E equals C. So if I take my protons and I subtract my electrons, I get my charge. Another way of saying that is the charge is simply the difference between your positive particles and your negative particles. I'll explain it more in a bit. But that leads us to our next vocab words. Ion, anything with charge. Doesn't matter, plus or minus, doesn't make a difference. Cation, some people call it, you hear people call it like a cation a lot. It's like a cation. That's, I think, the way to say it. That's the best way to say it, cation. That's how it's properly said. It's positive ion. A good way of thinking of it is the T for cat, looks like a positive. And then we have anion. That's a negative one. Kind of sounds negative, like anti or anion or something like that. It kind of sounds like it would be the negative thing of the group. And so I kind of think of anion just sounds negative, whereas cation, I think of the T as the plus. But cation is anything with a positive charge, doesn't matter what it is. Anion, anything with a negative charge, doesn't matter what it is. And then atom. We use the word atom. Up until now, we've been calling probably most things atoms. Now we're going to make a distinction. An atom is obviously an atom, but it has a charge of 0, therefore it is neutral. The moment an atom gains a charge other than 0, we call that an ion. So be careful with your definitions now. Atom and ion do mean different things. You don't want to confuse the two. A couple practice problems on this, and we're done. So I have 4 carbon atoms, or ions, I guess is the proper word. Well, I have an atom and 3 ions. We're going to figure out P's, N's, and E's. P should be easy. They're all carbon, they're all 6, done. N should be easy. We subtract. 11 minus 6, 12 minus 6, 13 minus 6, 14 minus 6, no big deal there. It's the electrons that's the problem. Remember, P minus E equals C. So this number in the top right-hand corner is called the charge. So plus 2, plus 1. The fact that they didn't write anything in means they're telling you it's 0, and then negative 2. So the charge is the difference between the pluses and minuses. Another way of doing it is P minus E equals C. So watch how it's done. So the first one, I'm going to take my P, which is 6. My electrons, so 6 minus my electrons is going to equal my charge, which is plus 2. So I'm essentially doing this formula. There's your answer, but let's look at the work first. So I'm doing this. I'm saying P minus E equals C, so 6 minus X equals plus 2. X is going to be plus 4, or just 4. It's that simple. That's all you have to do for charge. So in this case, 6 minus what gives me plus 1? Well, it's going to be 5. 6 minus what gives me 0? Well, obviously 6. And the last one, 6 minus what will give me negative 2? And the answer there should be 8. Yeah, don't worry about that. That negative 7's for the next line. So that's pretty much it. So that's how you determine charge. I like P minus E equals C all the time. It works every time because here's the issue. Sometimes you have P and you want to know E and you're given the charge. Sometimes you know P and E and they want C. Sometimes they give you the electrons in the charge and they want to know how many protons there are. So if you just do it this way, no matter what the scenario, you can figure out how many protons, electrons, or charge it has. You just need 2 of the 3 pieces of information. And then I just want to go over one last thing, which is how to view charge. And this is another way of viewing it. It's pretty simple. Think of it like this. If the charge is 0, that means it's neutral. That means my P's and E's are equal. So if I've got 6 protons, that gives me plus 6. If I've got 6 electrons in that same atom, that gives me negative 6. When I combine plus 6 and minus 6, I get 0. That's my charge. That's what charge really is. It's the difference between your positives and your negatives. If I have a positive charge, here's the trick. I do not have more positives because remember, it's still carbon, so it still has to have 6 protons. That's what makes it carbon. That's the atomic number, the fingerprint, the DNA, whatever you want to call it. But in order to get a +1 charge, what it has to do is have 1 less negative. So it actually would have 5 electrons, and that's where the +1 came from, and the reverse would be true as well. It would have 7 electrons in this case because it has a -1 charge, so it's going to have 1 extra negative over your positives. That's all charge is. And the last thing is a topic that we will use every once in a while, but it's not that big a deal, and it's very easy, so no big deal. It's called the nuclear charge. I don't even know why they include this, but they do, so we're going to learn it. It is the charge of the nucleus if you ignore the electrons. So if you think about it, go back to your very beginning of these notes, the only thing in the nucleus that has charge is protons. Protons positive, neutrons neutral, which means we can ignore them, and electrons we ignore because they're not in the nucleus, and this is only nuclear charge, not atomic charge. They are different. So all it really is the proton number. So for example, if you look up fluorine on the periodic table, it is going to be it's over here. It's going to be atomic number 9. That means it has 9 protons. So it's nuclear charge plus 9. That's it. The next one, I think I give you the charge. So let's say whether it did or didn't, it doesn't really make a difference. The +14 would mean it's atomic number 14, which would mean it's silicon. And iron would be 26 because iron is Fe and Fe is 26 protons. So when they say nuclear charge, just really in your mind think atomic number. That's all nuclear charge is because you're ignoring everything else in the atom that has charge except the piece. So that concludes this video. We will break down some practice problems in the next video.